Today we're going to have Djordje from here talking about the geometry and the arithmetic of non-spherical Maass.
Okay, super. Thank you so much for the invitation to speak and also for the lovely time at the Institute. And thank you all for coming. So I'll talk about some aspects of non-spherical Maass forms, and I'll just say this is joint work of several papers with Valentin Blomer, Gergo Harcos, and Peter Moga. And so the objects of this talk are Maass forms, and maybe I'll start by introducing those briefly. You've probably seen them before. Nevertheless, so suppose you can start with this as a purely analytic object. So you can take like X to be any compact Banyan manifold. And in your mind, if you want a concrete thing in your head, you can just take X to be your favorite compact arithmetic surface. And on this manifold, we have a notion of a metric. So we have some geometry. And corresponding to this geometry is a certain second order differential operator we call the Laplacian. Okay? And this Laplacian depends on the geometry that you put on this manifold X. So for example, my first example is not going to be the usual one. My first example is if you just literally take quotients of R squared, like you take compact quotients of R squared, then you would see the baby Laplacian del squared by del X squared plus del squared by del Y squared. Okay, if you've taught multivariable calculus recently, this is the one you've seen. And so if you want to do geometric analysis on this manifold, the building blocks of that would be the eigenfunctions of this. And so you would be looking at phi in L2 such that they are eigenfunctions of this operator, and I will always normalize them to be L2 norm 1. Okay, so if you have a compact Riemannian manifold, what will happen is that there will be a sequence of these eigenfunctions with discrete sequence with increasing energy levels lambda. And so for reasons that I'll kind of explain in a few minutes, you want to understand what these things look like for large lambda, right? So for high energy levels lambda, these things become kind of pretty wavy, pretty highly oscillating. And so one question that in particular I like to play with is I like to ask how large do the values of phi get? And the way to think about this question is, again, the total mass of this form is 1, but it is kind of a highly oscillatory object. And so you're basically asking about how is this mass distributed over this manifold. And the more classical question that people ask is literally the question of mass distribution. So that will be what people call quantum ergodicity or quantum unique ergodicity question. Somehow, what are the possible limiting measures of this mass distribution? But here I'm literally asking about pointwise values, right? So I'm asking, can it be that for a high energy level, you actually have some points where this phi is kind of extraordinarily large relative to its mean value, which is just 1. Okay, and so in particular, you could ask something that we call the sup-norm question, which is a question somehow you want to look at the sup-norm of this phi, and this phi maybe has some eigenvalue lambda, and you want to ask what power of lambda can you put here, right? So with what powers of lambda is this the correct estimate? Now, I think it is a fair question to ask when you get posed this question. It is a fair question to ask, why do we care, especially in a number theory seminar, why do we care about Laplace eigenfunctions? And why is this relevant? And so I do want to give a short spiel of this, which goes back to how you actually introduce this operator in multivariable calculus. Let me remind you, how do you sell this to students? Is that you look at a function And the way you define the Laplace operator is by looking at averages over small balls around your point. So in addition to the value at the point, you kind of look at what happens in a small ball and you average over the small ball. So what happens is that if you think about it in terms of like Taylor approximations, of course, it is going to be the average over a small ball is going to be very, very close to the value at the center point, but you want to look at the deviation. And what's going to happen is that the linear deviations are all going to cancel out in your spherical average. And what's going to be left is going to be quadratic in the radius, and the leading term of that quadratic is the value of the Laplacian at your function. Okay, why did I go through this exercise of saying this? Is that I want to kind of emphasize that the very definition of the Laplace operator involves averages over small balls. Okay, so this definition of delta is somehow attuned to averages over small balls. And so what this means is this definition is very highly attuned to the geometry, right? Because this definition sees the shape of your ball, right? Depending on the geometry, your ball could go like this, or it could go kind of like in a different direction, depending on how your geometry goes. And so this means that this operator basically sees, you could think about it as it sees the geodesic flow. It sees how the geodesic flow is going on this manifold. And so we say that this operator delta quantizes the geodesic flow. So then the idea is that somehow if you look at your manifold and you have the notion of a metric on this manifold, and you have the notion of how a particle flows, if you take a particle, you hit it in one direction, it knows where to keep going. If this geodesic flow exhibits some features, for example, if this particle kind of like flows around twice and then it just starts going on a periodic orbit, right? That's a stable feature of this geodesic flow. So the classical mechanics on this manifold have some embedded features. And the general principle, and physicists kind of in a nearby building can tell you a lot about that. The principle is that somehow whatever stable features you can see in classical mechanics should be reflected in the high energy eigenfunctions of the Laplacian, because somehow the Laplacian sees what's happening relative to the geometry. And so in particular, if you have, so I want to kind of switch to situations that are relevant arithmetically. If you look at manifolds that are negatively curved, so negatively curved manifolds, the classical mechanics are very chaotic. So there is a highly diffused picture, and so corresponding to that should be a highly diffused quantum picture. So the idea is that because a classical particle is highly unlikely to spend a lot of time in a small ball, it should also be very difficult for a high energy eigenfunction to be large around a particular point. And so, for example, on hyperbolic surfaces, well, this is a situation we are more familiar with. So if you look at hyperbolic surfaces, which are like portions of the upper half plane, maybe gamma is a discrete subgroup of SL2R. You can look at this sup-norm problem, and it turns out that somehow for purely analytical reasons, this can never be more than lambda to a quarter. I'm not going to spend time explaining this, but again, this is a baseline bound that doesn't see anything about the geometry. It's completely general. But again, because the geometric and classical mechanical picture here is very diffused, we expect that these point-wise values should not get this big. And so we might ask, like, can we actually save a bit from this? And this goes under the name of subconvexity problem here. And this has been studied. This has been studied in many works. It has a long history. This is a very special place to talk about that. So I'll just say here that if all you know about gamma is that it's a discrete subgroup of SO2R, so you're in a purely analytic situation, then we have nothing like this available. This is terra incognita, and I think it's generally kind of understood to be a hopeless problem. However, we do have a lot of progress in the cases when gamma is arithmetic. So for example, you could take gamma to be SL2Z if you want something concrete, and technically this is not co-compact, so there are issues that are related to that. And then I'm just going to sweep under the rug and say nothing about them. So I'm just going to pretend that this is co-compact for the purposes of this talk. And I'll just say that we do have an estimate. This was the estimate that started this whole business. We do have an estimate of lambda to 5 over 24 plus epsilon. Okay. And
there exists a basis.
sorry?
There exists.
There exists. Okay, fair enough. Oh, okay, you are absolutely correct. That so here when gamma is arithmetic for these eigenfunctions, we assume that they're eigenfunctions not only of the Laplacian but also of all Hecke operators, right? And then for that Hecke eigenbasis, we have this estimate. This is due to Ilyas and Sarnak back in the 1990s, and has not been improved, not for the lack of trying. I will say that many variations of this problem have been studied. And in particular, we do have variation for holomorphic cusp forms, which may be more familiar. So you could just take a holomorphic cusp form of weight k. Now that is not gamma invariant, but if you look at this quantity y to k over 2 times f, where f is a weight k holomorphic form, in modulus this is invariant under gamma, and so you could ask about the sup-norm of this. This is a well-posed problem. And again, the idea is that somehow high-weight holomorphic modular forms are a holomorphic counterpart of high-energy mass forms. And so here it turns out that k to 1/2 is the trivial band, and we actually have a much better improvement in this case. It's down to 1/2 of the trivial exponent. Okay, this is due to Shia and then later to Kayutin and Steiner on compact manifolds. All right, and so and there have been so many variations of this question that there's no way to do justice to everyone. But I do want to kind of step back before I continue, and I do want to say somehow that you can think about these as kind of totally different questions. You can think about this as, okay, you can ask this question for holomorphic cusp forms, or you can ask this question for mass cusp forms. But another way to think about them is that both of these are really just types of irreducible representations of the group SL2R, right? So you could be thinking about them as this is the sup-norm for principal series representations of SL2R, and this is the sup-norm problem for the discrete series representations of SL2R that occur in the same space. So you could just look at the space L2 of G mod gamma rather than just H2 mod gamma. And in this space, what you would see is basically half of the spectrum would come from principal series representations and half of the spectrum would come from the discrete series representations. And so you can think about them kind of like from a unified perspective. And this perspective is what I want to take up in this talk. So, so I promise that I'll talk about two groups in this talk. And so the first one that I'll talk about is SL2C. So I want to talk a little bit about what do non-spherical forms look like there. So I'll talk about non-spherical forms, SL2C.
Djordje, are they always, it's always like SL2, or you could put another, or do you consider other groups there? Or?
I will also talk about SL3R, but somehow, I mean, it's not like, oh, I just take another group and then I spend one afternoon and it's done. It's more like, yeah, you take another group, you spend another year and you're still not done. It's more like that, yeah. Okay, so, but I want to talk about this one in particular, and I'll say right away why. So what is the maximal compact in this group? It's SU2. Right, so the maximal compact here is SU2. And here's news about this maximal compact. It is not abelian, right? So, and because it is not abelian, that means that its representations are not just going to be one-dimensional. They're not just characters, but what's going to happen is that for every L that is like a non-negative integer, there will be a representation that I'm going to call tau L. It's finite dimensional, but it is not just one-dimensional. It's 2L plus one-dimensional. And this stands in contrast to the situation on SL2R, where the maximal compact is SO2, and we just have characters with respect to SO2. All right, okay, so that's kind of the first thing that's different. And then let me just describe the representations of SL2C. So So like irreducible admissible representations of SL2C. So this is what they look like. So there's obviously going to be the trivial representations, and then other than that, they are all principal series. All principal series. And they're induced. They're induced from a character on a parabolic. So basically, I can look at the parabolic, which is like z inverse anything here. So like in upper triangular matrices. And what kinds of characters can I put on this? So this is happening in SL2C. So these are going to be z and z inverse. And what kinds of characters can you put on z? Well, you can put the modulus to some power, and then you can also have the character, which is like the angular character of this. So those we call these characters chi nu p. So they send this to something like modulus of z to 2 nu, and then there's also z over modulus of z to some integer p, or actually 2p by normalization. And this kind of a representation I would denote by pi sub nu p. Only the unitary ones can occur in the L2 space for kind of obvious reasons. It's the L2 space. So only the unitary ones can appear. The way you can think about them is that for p not 0, so for p non-zero, nu has to be imaginary in order for this representation to be imaginary. For p equal to 0, when p is equal to 0, these are the more classical spherical representations, and they will contain a spherical vector, which we would call like a classical Maass form on SL2C. Once p is not 0, there are no spherical vectors, and there are no complementary series to worry about. So you can just think about nu as an imaginary parameter. This is the same nu that occurs in like Maass forms, like the 1/4 plus nu squared nu. Okay. All right. So there are these principal series representations, and what do they look like? So what does this representation look like? I can think about this representation space V. And as I said, once p is not 0, these representations do not contain a spherical vector. So we can actually decompose this. So we can decompose this with respect to the action of K, which is SU2. So K is a compact group, so I can decompose any reasonable representation into an irreducible sum of into a sum of irreducible reps. And so here the way it looks like is that this is going to decompose into a direct orthogonal sum of tau L isotypical spaces, and this L starts from P. Goes to infinity. So somehow the lowest K type that you will see corresponds to L equals P, and then they just start going up. And there's one copy of each. Okay, so they all appear with multiplicity 1. And then this space VL is a copy of tau L. Tau L, as I said, is 2L plus 1 dimensional. And you can actually further decompose this. You can further decompose this into like one-dimensional spaces, if you will. And the way you can do this is that you can look at this with respect to the action of, so K is a compact, and in particular, it will contain matrices of the form e to I theta into minus I theta, right? So this is, this is a group M that is a subgroup of K, and you can decompose this 2L plus 1 dimensional space with respect to the action of this diagonal subgroup in K, right? And it will decompose into one-dimensional basis. So this is what people call the Wigner basis of this representation. And this Q goes over all Q that are up to L in absolute value. So there's 2L plus 1 of them. All right, and then you can normalize these to norm the LQ. You can normalize them to be L2 norm 1. And so you can now, so basically, let me just take a step back. So what is somehow the simplest situation that I could possibly be in? So the simplest situation I could possibly be in is if P is 0. So if P is 0, then this sum starts at L equals 0. And so somehow the lowest weight vectors are those in V0. They are actually K-variant, and they are actual spherical Maass forms. And everything else that you see in this crazy description of the spectrum of SL2C is non-spherical. All right. So the type of a question that I want to study is somehow I would like to understand. For example, I would like to understand these forms phi L cube, or maybe you could also want to say, if I just want to look at them in this space, then I could look at a vector valued form, right? So I could also look at a vector valued form, big phi L, which consists of all of these phi L cube at once. Right? And so again, if P is 0 and L is 0, then what you're looking at is really just a spherical. It's a spherical Maass form, and it has its continuous parameter nu, and you could ask what happens for a large nu. So that is the classical sup-norm problem about which I talked about here. And it is well studied and well understood. It is not easy, but it has been done. But the question I want to ask here is somehow completely different. I want to kind of ask an analog of this weight level, of this weight type question, right? So this was a question for holomorphic Maass forms where I asked what happens for a large weight k. And so basically what corresponds to that is that I could ask, if I look at a representation pi nu p, and I ask myself what happens if I take p to be very large. And I don't really care about what happens with nu. In particular, I might as well just take nu to be bounded. Like if nu is literally 0, then those are like often like what we call cohomological forms. They can also appear. But I don't necessarily insist on nu being 0. Maybe I just take nu to be bounded so that so somehow nu is an uninteresting parameter, and I want to take p very large. So if I take p very large, then again, I will not see any spherical vectors here, but I can study the lowest weight vectors. And if you study the lowest weight vectors, that's exactly what you're doing in this situation, right? When you study holomorphic Maass form, sorry, edit that out. When you study holomorphic Maass forms, right, they are the lowest weight vectors in their representation, right? So you could ask about the situation when L is equal to P and it's actually very large. And that's the question that we want to study. So maybe I can go here. So we want to understand how large can this be? So how large can the sup-norm of phi L, and how large can the sup-norm of phi L cube be? Okay. And so these are basically, you could think about them as the weight aspect sup-norm problem here, or the way I like to think about it is I like to think about them as the large dimension aspect of the sup-norm problem. This seems to be kind of fairly untouched by the literature. And there is kind of, I think, a reasonable question to be asked. Why does the literature focus on spherical forms? When, like, I think from the point of representation theory, you should study the full spectrum. And this is the relevant question in kind of the more general spectrum. And whenever you approach a question like this, you should ask yourself, what is the baseline? And here, I'm not going to explain where this comes from, but the baseline bounds are L to 3/2, and then this is somehow, there's L of them, so you would expect square root of L less, and that is exactly, we can prove a bound like this, but this is the latter one, as far as I can tell, is far from trivial. Like this took us many months to get this one. Right, so these are like maybe the baseline bounds. And when I say baseline, I mean they're geometric bounds and they do not require any arithmeticity. Right? So you can take gamma to be any discrete subgroup of SL2C. And somehow the interesting problem is to break this, the barrier, to go below this. And those are our theorems that we have for SL2C. So I'll state them here. They're theorems, but I'll state them kind of at once. So we can prove for, like I said, so pi will be pi nu p. I will take the continuous spectral parameter nu to be in a compact fixed forever interval I. So you can think about maybe nu is no more than 1. So I'm not really interested in the size of that. And I'm interested in a situation when p is equal to L. So this is like this is the lowest weight situation, and we can prove the following bounds, right? So we can prove that this phi L at least I'm gonna be always restricting to a compact set. So maybe, let me just be clear here. So omega is gonna be a subset of G mod gamma, and it's gonna be compact. If your group gamma is co-compact, then this is somehow automatic, right? But if the group gamma, maybe this has finitely many cusps, and that's fine, as I just don't look at the values deep inside the cusps. So we can prove, we can go quite far below L to 3/2, so we can go down to L to 1 plus epsilon for the vector valued form. And then for the scalar valued forms, we have a couple of estimates. So we can prove that these scalar valued forms phi LQ, so we can go below 1 to 26/27, which is less than 1. I like it when your fraction is such that it's obvious that you're winning. Sometimes the fractions are such that you actually have to give decimal values. And we can do this for every Q up to L. So this is actually true for all Q. And then one interesting feature that happens, and I hope I get to say a few words about that, is that these estimates on these scalar value forms phi LQ are actually quite sensitive to the value of Q. That is not something we expected. And we actually get better estimates for two special values. So one is when Q is 0, and people tell me that this is what you should think about as the new form. So here we can actually win quite a bit more. So we get 7/8. And then we actually find that the most interesting case is the one when Q is plus minus L. And for these, we can do much better. We can go down to 1/2. Okay, so that's kind of, those are the kinds of estimates we can prove here. And so we're thinking about these as somehow being the high K dimension analogs of the SL2R response.
Right.
Yes.
Gamma arithmetic.
Sorry?
Which of these is it important that gamma be arithmetic?
Yes, absolutely. Oh, sorry, I didn't say this. Yes, so gamma should be. All right. So gamma should be arithmetic, and in fact, we only technically do it for this.
And if gamma were not arithmetic,
yes.
What would you be able to say, for example, about the last case when the Q parameter is at the end point?
I don't. That is an excellent question, about which we have literally thought nothing at all. So we haven't spent any time on that because we got so scared of how long this took. Like for a general Q, this was many months. We thought we would actually never be able to prove it. And so once we got this, we were like, we're just done with this, right? But that is a very good question. It will be interesting to see if in the collapse case you could do better. Yeah. Yes.
You said you just zero joined either, but if you went to like Eisenstein integers or some other ring of integers in a quadratic imaginary extension, like how sensitive are they? Not a very specific example.
Probably not very. I will say that for, especially I would say, I would be primarily kind of worried about this particular case, because here we actually use, quite a bit about the Rankin-Selberg L functions. Okay. And so at that point, the literature that we had was just available.
Oh, I see.
And we were not looking forward to generalizing that. So if you ask me, yes, of course, I'll shrug and I'll say, sure, it should work, right? But I do not want to write this down. All right. So then maybe I should kind of give you a little story about how do we prove things like this, right? So the standard tool here is what we call pre-trace formula. And I just want to set this up in general and give you a sense of what becomes different in this case, right? So the way you get a handle on individual values of mass forms is by something called pre-trace formula. So you look at what we call the automorphic kernel. So you sum over all gamma in gamma. You put a nice test function f. And you sum the values of f at G inverse gamma G, where G is your point of interest, where you're trying to estimate your form. And it turns out that somehow, so this is nicely gamma automorphic in G, so it will have a spectral expansion over an orthonormal basis. And what you're going to find with every phi, you will find exactly the value of phi of G squared and there will be a certain transform of this function f. And then there's also going to be the Eisenstein series contribution, which I will say nothing about, but it's typically easier to handle. Okay. Okay. So the first, so this is somehow almost a formality. And so the first step that you have to do is you have to understand this transform. So there's this transform that sends f, this transform f hat of phi. To understand it in this direction is not very hard, but somehow what you really want to do is you want to be able to go both ways. Because what you want to do in practice is you want to choose your f. So you want to choose f so that this is large at your preferred form phi. So the idea is you have one form phi for which you're trying to estimate this. And then for all the other forms, if you get positive values, they're kind of just waste, right? So you would ideally you would like to isolate your form phi as much as you can, right? So you want to choose f so that f hat is large at your preferred form. And then you just kind of, that gives you a good handle. You get like a large coefficient times what you want to estimate from above. And then you somehow have to see what happens on the other side, depending on your f. So that's why you have to be able to kind of go backwards. And so at best, what you can hope for, well, this is kind of highly schematic, but just kind of want to say. So at best, what you can hope for is that you are so lucky that your f concentrates so nicely that only the identity contributes here, or at least that the identity dominates. The identity you will never be able to avoid, but maybe you can kind of really cross your hands, your fingers, and you can hope that the identity dominates. And then what you can hope for is that on the spectral side, you are able to localize to your preferred form. So to localize to maybe phi in a representation pi nu p, and maybe you can hope to localize to p being exactly your value. So maybe plus minus L, and maybe you can hope to localize to nu in an interval essentially of size 1. And you cannot hope to isolate to less than an interval of size 1. This is essentially the Heisenberg uncertainty principle. If you try to localize to less here, then what happens is that on the geometric side, it just explodes your loops completely. And so if you kind of follow this, if you follow this faithfully, and if you are actually able to execute all of this, that's what buys you the trivial bound. Okay, so please note I have used no arithmetic yet. Like this gamma can be any discrete subgroup so far. All right, so how do you use arithmetic? Is that you use Hecke operators. So let me go to that. So first idea is that you can also, what you can also do to this formula is that you can now attack it with a Hecke operator. Let's say you attack this with a Hecke operator Tn. And if you do that, then what's going to happen is that you're going to pick up the Hecke eigenvalue of phi here. And then here, instead of summing only over gamma, you will expand the range of matrices over which you're summing. So this might lead to something like, so the schematic of this is that you introduce what's called an amplifier. So you use Hecke operators Tn, you put some coefficients xn, and what you pick up with every form phi is basically the transform of this sequence x relative to phi. There's going to be the transform of f relative to phi. It's the same as before. And what's going to happen on the other side is that now you're going to be summing over all n. There's going to be this coefficient xn, and there's going to be sum over all gamma in gamma n. And what is gamma n? Let's say if gamma is SL2z or SL2z of I or something like that, this will typically be something like the set of matrices of determinant n. Right? So rather than determinant 1, you get matrices of determinant n. And then you get the f of g inverse gamma over square root the determinant times g. So that's how it generalizes. And so then, again, the philosophy is that you pick up, so you pick f and x to emphasize your form. So you have your favorite form in the world, and you pick both the test function and the amplifier to kind of additionally emphasize your form. And then on the other side, now you need to understand what happens on the other side. That means you get a counting problem. So this is common in all sup-norm questions. So you get a counting problem. And so in the classical spherical sup-norm problem, what ends up happening is that so this function f, when you're trying to pick out just spherical mass forms, then this function, what corresponds to that on the geometric side is this function f has to be bi-k invariant, right? And so, so what ends up happening is that you need to understand this function f ends up localizing close to the compact. And so you need to understand for how many matrices is this very close to the compact. So the classical counting problem that you get here is to, so in spherical case, you would need to understand the number of these matrices gamma and gamma n so that this matrix G inverse gamma over square root determinant gamma G, the distance from this to the compact is small, right? So you give yourself a small distance delta, and you need to understand for how many Hecke correspondences that this fall within delta of k. Right? So this is somehow the classical counting problem that you encounter in the spherical sup-norm. Any questions before I actually say what we have to do? All right. So okay. So in the case of non-spherical forms, the setup is similar. But as I said, the first thing that you have to understand is we have this transform from a suitable test function f to the weight that it will assign to your representations, right? So for this, we need to understand something called tau L spherical transform. And tau L is this K type that you're trying to pick out. Okay. So for just to be clear, for L equal to 0, so if you were in the spherical case, the transform that I'm about to talk about is the classical Selberg-Harish-Chandra transform. And for those of us in analytical number theory, it is the transform we know and love. We could write it down, and it's kind of very well understood. So in general, the way this transform works is that, as I said, there's going to be a transform. It's going to be attached to representation. So it's going to depend on these parameters nu and p. And it's just going to look like this. It's going to be the integral over g of f of g against a special function. This is literally a special function. Call it phi nu p L of g. And when I say a special function, I just mean something that you could in principle find in Grotstein-Rijik or something like that, right? So this is what it looks like. So you have these parameters nu p and L, and it's really the trace of this operator. So you start from phi nu p.
Which special function is it?
I'm about to write it down.
Oh, what would Grotstein-Rijik?
No, it's probably not in Grotstein-Rijik, but I'm saying it could be. It has that much content, right? It's like.
So what is, well, I'm curious what you would define a special function as.
It's something that you can write down in terms of coordinates, and it has like finitely many symbols. Yeah, okay. Okay, so it's trace of pi nu p of pi L bar, and then pi nu p of g, and pi nu p of chi L bar. And what is chi L? It's the character of this representation tau. Okay, so it's something that, you know, for every matrix G in SL2C, you can just feed it into this and it will spit out a number. And this is what we call the spherical trace function.
Doesn't have a nice closed form, is that right?
It depends on what you call a closed form. I'll write it down. So I'll just say this is called the spherical trace function. And somehow understanding this spherical trace function is somehow most of the work that we have to do, right? But it does have reasonable formulas, but somehow whether it's a closed form, I don't know. So I'll tell you a little more about what this looks like later on when I talk about SL3R, right? So maybe I'll just I will spare you the details, but I'll just somehow say that it is given by an integral. An integral over k, and then you just somehow have to understand where are the contributions that you get. Okay, so I will rather just tell you what comes out of this calculation. Okay, what comes out of this calculation is that you need to understand. So as I said, you need to understand this transform between f and f hat, and in particular, you need to understand how to go back. And going back involves again this same spherical trace function And so what you need to understand is you need to understand the concentration properties of this spherical trace function phi nu p L. And in general, if you also want to study those scalar valued functions, then there's going to be an extra parameter q. So this is really fun. They're like, 4, 6, 8 nested integrals, depending on how you parameterize things. But okay, so some of us think that that's fun, and we did that work for you. And so I'll say what the concentration properties are, but before I say that, let me just remind you why I need that. I need it because in the end, this is going to go into this free trace formula setup. And if I understand where these functions are large, then that is where I need to understand the count of these matrices gamma. So I'll need to understand how many matrices gamma fall into the range where this spherical trace function is large. That's ultimately what happens. And that becomes an arithmetic problem. Okay?
Pi L is the character
of tau L. And tau L is just the 2L plus 1 by 2L plus 1 rep of K. All right, so before I say anything else, I'll just remind you. So in the case of the spherical sup-norm problem, this was all about the distance from the compact, right? And this is a major, in particular, this is a major obstacle in the spherical sup-norm problem, right? So, so here is what we find here. So here we find that there are different kinds of concentrations, not just to the compact. So there's concentration to somehow some special submanifolds of SL2C. And this is somehow the fun part for us. So remember, SL2C is 6-dimensional. Just keep that in mind. Okay. So we will need, some of them will concentrate just to the identity. The identity is a 0-dimensional submanifold. Some of the estimates will depend on the distance to what we call S. And this is the union of the diagonal matrices in K and the off-diagonal matrices in K, like this. Okay, and both of these are 1-dimensional. Okay, so this is the centralizer of A in K. There is a good description of this set. Okay, then so this is 1-dimensional. Then there's the 2-dimensional set of all diagonal matrices. So all diagonal matrices in G, that's a 2-dimensional set. And so again, some of these spherical trace functions will localize close to the diagonals. Some of them will localize close to the compact, which is SU2. And then some of them, this is the funnest one, some of them will localize to the 4-dimensional manifold N, which is the set of matrices ABCD in SL2C, such that A and D are of the same modulus, and B and C are of the same modulus. And I have to say, I've never before in my life seen this 4-dimensional manifold in SL2C. Okay, but it turns out that somehow the concentration is literally to one of these, and then you are led to the counting problem. Then you are led to the counting problem of please count all matrices in SL2C of not in SL2C. Please count all 2x2 matrices with Gaussian integer entries of determinant n, such that their distance to one of these things is less than or equal to delta. Okay, and that becomes kind of a fun Diophantine counting problem, and you end up, I said 2x2 matrices in SL2C, so that means I have, 2x2 matrices with complex entries, so that means I have 4 Gaussian integers, so that means I am looking at 8 real variables, right? So these are counting problems in an 8-dimensional space, and you're looking at things like count things that lie in a thin wafer, count things that lie close to a cylinder, etc. Right? These are kind of fun geometry of numbers problems that we have to solve. All right. Any questions so far? All right. So if not, then I want to say I want to finally say what this becomes in SL3R. That will give me an opportunity to tell you a little bit about what this spherical trace function looks like. So, yeah.
Q function then means that you replaced pi L by the projector to that vector.
Now, what we I would be very happy to see kind of a nice and beautiful description of that. All we really did with this is that we literally took this one and then we integrated it further against like the the Q character of the diagonal on the compact. Okay, so we did it somehow by force, right? And we paid the price in like horrendous estimates. There's probably a nicer way to do it. All right, so I want to say what this looks like in SL3, and there's some fun things that happen there as well, right? So what do these look like? So we deal with principal series representations of SL3R. So SL3 has a maximal compact, which is SO3, and that is conveniently basically the same thing as SU2. So in terms of those representations, that's kind of similar. And so these principal series representations, they are induced from a parabolic. And what type of parabolic can it be? You can induce from the 1 + 1 + 1 parabolic. And those, if you induce from a unitary character on the 1 + 1 + 1 parabolic, you will just get spherical mass forms. Or you can induce from the 2 + 1 parabolic. And these are the ones that give us the non-spherical forms, right? So these are induced from the 2 + 1 parabolic. So here I will need one little Iwasawa decomposition. So this group is SL3R, and I can think about it as KMAN. So I'll just specify for you what is what. So K is just SL3. M is, in this case, is the group of matrices that look like SL2R, and then just one here. And then otherwise they're 0 and 0. A is the group of matrices that look like, so they're like scalar matrices here, and then you just compensate for that scalar here. And N is the block upper triangular unipotent matrices. So like this 1, 1, and then some vector here.
You said you're considering these two groups because at the compact, this SO3 and this U2 have some.
Are you asking why 2 + 1?
No, the reason, like, I don't know, for someone who doesn't work on this, like the reason you were looking at SL2C and SL3R, you're saying is going to be because like this pair has to do with the compact.
The reason why I'm looking at these two groups is that they are the first two groups I could think of with a non-abelian maximal compact. Okay. Okay. In particular, SL2C was the first one. I spent 5 years on that one, and then it was time for the next one. Okay.
So you went from U of 2, and then you're like, okay.
And then I'm like, oh my God, there's another group where it's the same compact. Yes. Okay. All right. So now maybe I should keep this here and go to the next board. So I want to write down with this decomposition, I can actually write down a formula for this spherical trace function. I was asked about this, so that gives me a good excuse. So this spherical trace function, it will depend on this tau L type, and then also on the representation pi nu p, and I will only look at the case when equals L, right? And this is how like we have a formula for this as at a matrix X, and it looks like this. So 2L + 1, that's just normalization. It's an integral over K. And so then we actually just do some things with K inverse XK. So there's 3 factors. There's one factor, which is just of modulus 1. So I encourage you not to think about this factor too much. So there's this factor. Then there is a factor that I'm going to call phi chi L delta L of mu of K inverse XK. And I'll say in a second what this is. And then there's going to be tau L of bold K of K inverse XK dk. And what are these things? Okay, so first of all, what is mu of K inverse XK? That means I take K inverse XK and I look at its M component. Okay, so now when I look at its M component, I essentially have a matrix in SL2R. And what does this do to a matrix in SL2R? This is just the trace function on SL2R for weight L discrete series representation. Okay, so this looks like explicitly, I can write it down for you. It's something like 1 over A + D minus I times B minus C power L. And maybe there's a 2, just as a normalization factor. Okay, so this is just again, this is the character of the weight L discrete series representation of SL2R. And so what this does is that this localizes to matrices that are effectively in SO2. So this factor localizes to the situation where to the situation where this mu is in SO2 plus big O of 1 over root tau. So this matrix has to be close to SO2 plus just a little bit. So this mu factor should be something like SO2 matrix times 1. And then what is this tau L? Well, tau L is literally just you can just think about it as the matrix of the finite dimensional representation tau L. And I need to actually put the LL entry of that. And what is this bold K of this? That means you compute the K part of this matrix. Okay, so you compute the K part. This is now a matrix in SO3. You feed it into this matrix tau L, and what this localizes to is that it localizes to matrices where K inverse xk is upper triangular plus big O of 1. So there's a very strong localization that happens from each of these factors. And so what ends up happening is that, okay, so so after you kind of like spend some time staring at this formula and getting your bearings, you realize that, okay, so this is what needs to happen. So first of all, I look at this matrix X, and I need to ask myself, does it ever happen that I have a K conjugate of X such that its mu part looks like basically it's an SO2, and such that its K part is upper triangular? And if that never happens, then this integral is essentially integral of 0. Like it's like L to minus 100. It's super small. And on the other hand, if it does happen, then I have to ask for how long. So somehow, what is the measure of the set of x's such that both of these support conditions are satisfied? And while this support is satisfied, I have to ask myself, is there any oscillation that happens and that there's an additional cancellation from that? Okay, so you do that fun work, and this is what ends up happening. I thought this was really, very neat. So you remember how I got the crazy localization over there to some submanifolds of SL2C? So a similar thing happens here. There will be 3 submanifolds of SL3R that are of interest. SL3 is, let me not say something stupid, SL3 is 8-dimensional. Right? It's like 9 minus 1. So SL3 is 8-dimensional, and inside it there will be 3 submanifolds of interest. So there will be the identity. There will be a fun 4-dimensional manifold that I'm going to call R. And so this is a submanifold I can explain geometrically. So these are the SL3 matrices that are K conjugate to matrices of the form, so basically the product of these two, right? So it needs to be matrices of the form, I have GO2 here, and I have like an entry here, and otherwise it's 0, 0. Okay, so let me talk about what is this. So when I say that I can describe my matrices up to K conjugation, that means that I can describe what these matrices do geometrically, right? So what these matrices do geometrically is that they have one plane. There are 3x3 matrices, so I can think about them as transformations of R3. So there are matrices that rotate in one. They rotate in one plane, and then they're additionally allowed to dilate in one direction and then somehow contract in the other direction to compensate for that. Does that make sense? It's like a rotation dilation, right? And in particular, this contains K, right? So K, the maximal compact, is a subset of this because every isometry in R3 is a rotation around an axis. So this is like a slight extension of the isometries, and you can compute its dimension, and the dimension is 4. So this is only 1 dimension more than K. And it's a very interesting submanifold. Again, it's a submanifold of unimodular transformations of R3 that look like rotation dilations. Okay, and then there's another submanifold that I'll call S, and they are SL3 matrices that are K conjugate to something that looks like GO2 star, and then also a star is allowed here. So these are, you're allowed to rotate, dilate, and then you're also allowed to shear relative to this plane. So the dimensions here are that this is dimension 0, this is dimension 4, and this is dimension 6 in the 8-dimensional SL3R. And so what we can show, maybe I'll kind of go here, is that we can show the following estimate. So we can show that this spherical trace function phi, so it has tau L and it has pi, nu, and L. We can prove an estimate like this. So first of all, it depends on the distance to the identity, and it decays like 1 plus L times the distance from G to the identity squared. Okay, so how do you read this? You read this as if G is within 1 over root L of the identity, then there's no decay. And then if G starts going farther and farther away, then there is decay. In particular, if G is somehow at distance 1 from the identity, you have like 1 over L. Okay, and then there's also times 1 plus root L times the distance from G to this submanifold R. So again, this means that if this matrix G, for example, if it's at a generic distance 1 from the identity, then there is no savings from here, but you will get the square root of L savings from here if your matrix is far from the manifold R. Okay, so the spherical trace function decays like this, and there's an extra thing, which is that also this thing is super small, like it's less than L to minus 1,000. If G is not within 1 over root L of this, right? So basically, there's like 3 levels of size of this spherical trace function. It is the biggest at the identity, and then it starts decaying away from the identity. But in addition, it wants a little bit more. It's a little bigger along this 4-dimensional manifold R, and then it also starts decaying away from the 4-dimensional manifold R. And then finally, it is essentially supported on this 6-dimensional manifold S, and then just dies away from S. So this is the concentration of this, and we believe that this is optimal. This is very hard to numerically test because of the dimension aspect and everything, but we have tightened this, and it looks to us like this is actually the truth. Okay? So this is actually the description of the concentration of the spherical trace function on SL3R. And finally, I should tell you a few words about what do we do with this, right? So this leads, and for this I'll just have like a minute or two, so I'll just say that this leads to the counting problem. So this leads to the counting problem of matrices gamma with entries like, so 3 by 3 integer matrices gamma, such that so we need to kind of account for the Hecke operators. And so in this case, it turns out that the relevant thing is that we need to look at matrices gamma of a certain Smith normal form. So here, so this gives us access to, so what we will know about these matrices is that we will know what is the determinant gamma, and we will know what is the GCD of all 2 by 2 minors. So we will have this arithmetic information about the gamma, and then what we will need also is that gamma over the cube root of determinant of gamma should actually be close to, and here I mean G inverse this times gamma, it should be close to these submanifolds. So to the identity, to the submanifold R, and to the submanifold S. And so depending on how good of accounting estimates we can get on this, we actually get a sup-norm bound. So here I will be extremely brief, and I'll just say that we have found that actually we do not know very well how to use these manifolds R and S. It's just arithmetically it looks very forbidding, and we only know how to use the distance from the identity. And for the distance from the identity, what we found is that, interestingly, if the distance from the identity is somewhat large, we find that the most efficient thing is to turn the counting problem backwards and to go back to the spectral side. So we use the pretrace formula backwards. And this allows us to treat all the cases when this distance from the identity is somewhat large. And so we only end up with the cases when the matrix is actually very, very close to the identity, and then the counting problem becomes very, very kind of quote unquote easy, right? I mean, once you've seen like 200 counting problems in your life, then this one is not so hard anymore, right? But it's only because we are able to reduce the problem to the ones where the distance is fairly small. And I'll just say, I mean, if anyone cares for the exponents, the bound that we got is, so the baseline bound in this case is 3/2. That's the one you need to bound, and we're able to, you need to beat, and we are able to beat it by 1/14. I mean, of course, the exact exponent is somehow meaningless, but somehow this is what comes out with methods. Okay, and that's all I'll say. Thank you so much.
That's good for Djordje.
Yes.
At the
Group
beginning,
A.
yes, in my own group over
Yes.
here. I've got like, there's another.
Oh, that's right. Yeah. Okay.
When at the very, so this is from the non-expert question over here in group
Yes.
A. At the very beginning, you're like, okay, so you're asking how big these values can get, but what's the, like, what is there like an application or why, like, because there's like a lot of interesting stuff that goes into it, but why?
There are
Why do I want to know?
There are analytic applications and there are arithmetic applications.
Okay. Can you give an example?
Yeah, sure. So for
One that I
example,
might-
an analytic application would be something like, for example, when people study the number of nodal domains, right? So you could ask the question of, let's say on the upper half plane, you're looking at the modular surface and you're just looking at, standard spherical mass forms, and you can look at the nodal lines and you can ask how many domains are there.
Okay.
And there are very well established conjectures in this area. And somehow I think that the only way we know how to bound this is, I mean, you start from the boundary, you look at what's happening on the boundary, and at some point you need an estimate of the sup-norm in your proof. I do know of an arithmetic applications to Falting's delta function, but I will not be able to say much more about that.
Okay.
Yeah, stop there. I will say, kind of personally, I'm just drawn to this somehow from just a Platonic point of view. I'm like, this is very, very interesting. And also, like, I look at these, the pictures are actually fascinating. The pictures of these eigenfunctions, I told you, so these eigenfunctions are whatever interesting analytic features you see in these eigenfunctions, it's supposed to mirror what's happening in the classical mechanics. So if you look at the pictures of these things, in the cases, let's say you give yourself a billiard where there are somehow embedded stable geodesics, you will absolutely see them in high energy eigenfunctions. I mean, you plot this in Mathematica and you just see you see like a function which somehow chooses to be large along a closed geodesic. And the pictures of mass forms are also very interesting. They are of course more chaotic, but you can absolutely see the closed geodesics are somewhat visible in these pictures, right? So for me, there's just this question of somehow how much can this thing concentrate? And the QE people ask questions such as how does the mass distribute as like somehow in the sense of probability theory, right? Yeah.
So if you looked at the analog of this phi where L is 0 and where nu is allowed to vary,
Yes.
would you still see this sort of hierarchy of concentration or?
No, that's a very good question. I will also say somehow I have my personal reasons why I wanted to study this, and it was exactly because I wanted to break this concentration to the compact. So what happens in the spherical problem that you're asking about, so you keep L and P to 0 and you just look at large nu, is that because you're looking just at the spherical spectrum, the test function, the thing that goes on the geometric side, is going to be bi-K invariant. And what that means is that all the concentration will be in terms of distance to the compact. I mean, that somehow it's almost like a tautological, what I just said, right? So so for the case of group SL3, or really for all general groups SLN, this has been studied. And the way you study it is that you prove a certain decay estimate, and the decay estimate is that your geometric test function is full size along the compact and then decays at a certain rate as you move away from the compact. That's always how it looks like. So it's always the compact. The reason why we're seeing things that are not the compact is that we've moved away from the spherical sup-norm problem. And so the thing doesn't have to be k-invariant anymore. So that's why you're seeing different manifolds appear.
Have you sort of tried to relate these sets to the geometry of the coadjoint orbit?
That is, I haven't, but I know who has. Paul Nelson told me this after the first talk I gave on this topic. Yes, that would be something that you and I should talk about, hopefully. Yeah, it certainly has something to do with that.
Right. Well, one could imagine that associated to your data is a kind of blob on the coadjoint orbit, and then you have to look for the set in the group which preserves that blob. And that should have some relation.
Yes. Yeah. There is almost something, I mean, especially the first paper, the SU2 paper that we did, we kind of did it very sines and cosines. Like we really did it very, very explicitly, right? But you know how it is when as you work more and more on the problem, you start seeing somehow what is happening structurally. Yeah. Yeah.
Does this phi satisfy an ODE sense, or is this no ODE?
Yes. Yes. So I mean, in particular, did you ask ODE? No, it's going to be a PD.
PD.
No, of course, a PD. Yes, I mean there will be more than one differential operator that is involved. Like I can speak more with confidence on SL2C, right? So on SL2C, there's going to be two Laplacians. There's going to be the Laplacian on the group, and there's going to be the Laplacian on K, and there will be relevant eigenvalues for both of those. And maybe I'll say somehow fun fact that I didn't mention in SL2C. So in SL2C, these spherical trace functions, so the representation has two parameters. There's like nu parameter and p parameter, right? And fun fact, there is a weird symmetry between nu and p. Like there should be no symmetry between them. One of them is continuous and one of them is integers. But it turns out that there is actually a symmetry, and the values of phi nu p are actually, this function is literally equal to the function phi p nu. It makes absolutely no
I
sense.
think it's like SL2. If you go to the algebraic closure, it becomes SL2 times SL2.
Okay, fair enough. Surely there's somehow a big picture version of this, but somehow when you're working with this, what this means is that if you think about the corresponding transform on the spherical, sorry, on the spectral side, right, where you think about these phi nu p sort of like as a collection of functions of nu. So for every p I get a function of nu. What you learn is that there's some weird symmetries which somehow if I know phi nu p for one p, this now impacts the values for all other p at some special points. And so in particular, we had to solve, so somehow solving, to understand the spherical transform completely, you have to be able to go from the spectral function to the geometric test function. And so this is essentially a generalized Paley-Wiener problem. And we had to solve this Paley-Wiener problem where we had all these weird connections. So when you're working with these spherical tests, with these spherical functions, right? You're used to kind of usually just thinking about them on the tempered axis, because somehow that's the only place where the Plancherel measure, where there is Plancherel measure, and so you're kind of used to thinking about them that they only matter there. But it turns out that for the CC infinity Paley-Wiener problem, you actually have to think about the entire analytic continuation, and some values that are very far from the tempered spectrum matter because of this weird symmetry between u and p. And this is something that does not occur on SL3. This is just an SL2C phenomenon as far as we could tell. In general, these are known as Arthur-Campoli relations, and it's complicated.
More questions? That's that.
Okay. Thank you.